Now let's focus on RC low-pass filters. An RC low-pass filter is designed to allow low-frequency signals to pass through with little attenuation, while gradually reducing the amplitude of higher frequency signals. In this configuration, a resistor and a capacitor work together so that at low frequencies, the capacitor presents a high impedance, resulting in the output voltage closely following the input voltage. As the frequency increases, the impedance of the capacitor decreases, which causes more of the high frequency signal to be shunted to ground. This behavior creates a smooth transition between the pass band and the stop band, with the cutoff frequency marking the point where the output drops to about 70.7% or minus 3 decibels of the input signal. Quick definition here. What is pass band? You probably already know about it, but just in case. The range of frequencies that a filter allows to pass through with minimal attenuation is pass band. These frequencies remain largely unchanged by the filter. And the opposite of pass band is stop band. The range of frequencies that a filter significantly attenuates or blocks, reducing their amplitude substantially, is called stop band. Here is the schematic that represents a basic RC low-pass filter. In this circuit, the resistor is connected in series with the input voltage, while the capacitor is connected between the node after the resistor and then the ground. This arrangement forms a voltage divider where the capacitor's impedance decreases with increasing frequency, leading to signal attenuation at higher frequencies. In this example, the input voltage source is an alternating sine wave. Let's have a look at the mathematics now. If you are curious about the underlying mathematics that describe the behavior of the RC low-pass filter, which I encourage that you should be, then continue with this lecture. Otherwise, you can find the most important takeaway formula, which is the cutoff frequency at the end of the segment of this lecture. The behavior of the RC low-pass filter is characterized by its transfer function. The transfer function is given by this formula here. To analyze the filter's response to inputs, we substitute the complex frequency S with J times omega, where omega is the angular frequency in radians per second. Now here's another definition. You might be wondering, what is a complex frequency? So the complex frequency S is a variable used in the Laplace transform, defined as S equals sigma plus J times omega. It combines an exponential decay or growth component, which is the Greek letter sigma, or denoted by the Greek letter sigma, with an oscillatory component, which is the omega, making it essential for analyzing the behavior of linear time invariant systems. Thankfully, as a new student of first order filters, you don't need to learn the concept of complex frequency S to be able to understand how these filters work and to be able to use them. You might also be wondering now, what is the Laplace transform? So the Laplace transform is a mathematical operation that converts a time domain function, f parenthesis t for time, into a complex frequency domain function, capital F with S as a parameter, where S equals sigma plus J times omega. This transformation simplifies the analysis of linear time invariant circuits by turning differential equations into algebraic ones. For circuits such as first order filters, the Laplace transform allows us to derive transfer functions, analyze stability, and predict transient and steady state behavior efficiently. The substitution here results in this formula for the transfer function, and the magnitude of the transfer function, which represents the filter's frequency response, is determined by this formula here. At low frequencies, where omega times RC is much smaller than 1, the magnitude approaches 1, meaning that the output is nearly equal to the input. As the frequency increases, the term omega times RC becomes significant and the magnitude decreases accordingly. The cutoff frequency defined as the frequency at which the output drops to 1 divided by square root of 2 of the input, which is approximately minus 3 decibels, is given by this formula here, where Fc, which is a cutoff frequency, is equal to 1 divided by 2 times pi times R times C. The mathematical model is derived using the voltage division principle, whereas the capacitor's impedance is expressed as the fraction of 1 divided by J times omega times C, making the filter's response inherently dependent on frequency. Here is a Python script that generates a plot of the filter's frequency response. The plot illustrates the signal attenuation in decibels as a function of frequency that highlights the gradual roll-off characteristic of the RC low-pass filter. When you execute this code, it produces a plot that shows that the filter maintains a flat response at low frequencies and then begins to attenuate the signal progressively above the cutoff frequency. The red vertical line marks the cutoff frequency, which is also calculated by the script. Using this code, you can experiment with various values for R and C to see how they affect the frequency response of the filter. In summary, the RC low-pass filter is a foundational circuit that illustrates several core concepts in signal processing. The filter consists of a resistor in series and a capacitor to ground, forming a voltage divider whose behavior changes with frequency. At low frequencies, the capacitor acts as an open circuit, allowing most of the input signal to appear at the output. But at higher frequencies, its decreasing impedance diverts the signal to ground. The transfer function and its magnitude mathematically describe this behavior. The cutoff frequency defines the boundary between the pass band, where the signal passes with little attenuation, and the stop band, where the signals are significantly reduced.